Deep learning methods show great promise for classification of medical images to help healthcare diagnostics be faster, more effective, and at a lower cost. We implemented a model to classify 14 different pathologies from chest x-rays, including localization with class activation heat maps. The ChexNet model detected pneumonia with F1 scores that exceeded those of practicing radiologists, and our model achieved equivalent AUC values. Additionally, our model outperformed ChexNet on 4 pathologies, with AUC greater than 0.8 on 9 and greater than 0.9 on 2, emphysema and lung hernia. Transfer learning is a bootstrapping technique where a model trained on one problem is applied to a different problem that is similar in some way. Image classification is ripe for transfer learning, and winning models from the ImageNet competition are a common starting point. Our model was initialized with the weights of DenseNet 121 BC, pre-trained on ImageNet, then retrained end-to-end using different optimizers, specifically SGD versus Atom. We also experimented with different augmentation strategies, both with random flipping and without. We utilized multiple public cloud resources for our training, namely Collaboratory on the Google Cloud Platform and Amazon SageMaker on AWS. We used Spark and Scala for our big data preprocessing code and Keras and PyTorch for training the models. The authors of DenseNet report 4 main advantages of dense connectivity. It avoids vanishing gradients, the diversified features rather than correlated features, fewer parameters, and the classifier layer can use all features, not just the high-level ones. The DenseNet architecture consists of a series of dense blocks separated by transition layers with classification at the end. Each dense block has a series of units, and each unit within a dense block has the output channels of previous units concatenated. Here's an example of a dense block containing 4 units followed by a transition layer. The BC variation of DenseNet includes a bottleneck. In this variation, each unit within a dense block has 2 layers, a bottleneck layer to reduce the number of channels, and a composition layer with a wider convolution for feature learning. Each transition layer has a batch norm, followed by a 1x1 convolution and 2x2 average pooling. The 121 designation comes from the total number of layers. Our best results were better than ChexNet for 4 of the 14 pathologies and close in all of their cases. To our surprise, our results were better without random flipping. This could be due to a class imbalance. An improvement might be had by only augmenting underrepresented classes. Wilson and collaborators showed examples of adaptive methods that generalize worse than SGD and suggest reconsidering their use to train neural networks. We obtained better AUC values using SGD versus Atom for 12 of the 14 pathologies. We also pursued localization in addition to classification. Classification labels what is in the image, whereas localization identifies where it is in the image. An activation map is the output of a particular convolution layer. Considering only the class of a single pathology, we can convert the weights into a heat map. This heat map localizes infiltration. Clear air shows darkly on X-ray images, and whiter areas indicate denser material. A pulmonary infiltrate is a substance denser than air, such as pus, blood, or protein, which lingers within the parenchyma of the lungs. This class activation heat map sharply highlights the entire right lobe for presence of infiltrates in red. In contrast, the left lobe is free of infiltrates and colored blue. We compared training time on Amazon SageMaker. Training on CPU took around 16 hours, whereas GPU took around 4. In summary, transfer learning reusing existing models unrelated to X-rays can dramatically decrease startup barriers, allowing results equal to and exceeding trained radiologists. Heat maps enable verification of model focus and can be a learning tool for radiologists to help identify what may lead to a diagnosis. We learned tremendously through this project and our earlier assignments and greatly appreciated this learning opportunity.